Hello and welcome to this video. Today we are going to discuss the number system and properties. First you see natural numbers 1, 2, 3, 4, etc. up to infinitive. These are called natural numbers. We can also call these numbers as counting numbers, and that is the basic need, so we call them as counting numbers also. If you write these numbers in a set, you write all these in a set 1, 2, 3, 4, etc., 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 up to infinitive. This set is known as the set of natural numbers. It is denoted by n. N represents the set of natural numbers. Now later on, we find the need of 0. How? Let us see an equation. X plus 5 is equal to 5. What is the solution to this one? You know we solve these linear equations in one variable. Let us see what is the value of x. X is equal to 5 plus 5 becomes minus 5. This side when you take 5 minus 5, 0. X is equal to 0. So the value of x is 0. That is the solution to the given equation x plus 5 is equal to 5. This 0 we can't find in the set of natural numbers. That means we need another set of numbers in which 0 is present. That's why they defined another set of numbers including this 0. And they wrote as 0, 1, 2, 3, 4, etc., etc., up to infinitive. See, they named these numbers as whole numbers. What is the difference between these two? See, in the set of natural numbers, it starts with 1 and ends in infinitive. But in the whole numbers, you see, they start from 0 and in infinitive. That means all the natural numbers are present in these whole numbers. If you want to write them in a set, we can write them like this. The set of whole numbers, we call them the set of whole numbers. 0, 1, 2, 3, 4, etc., etc., up to infinitive. This is the set of whole numbers. It is denoted by capital letter W. W stands for whole numbers. The set of whole numbers. Later on, in the course of time, we find the need of some negative numbers, negative integers rather. See, how does the need arise? To solve the equations x plus 3 is equal to 1. This type of equations. X plus 3 is equal to 1. What is the solution to this one? X is equal to 1 minus 3. That is equal to 1 minus 3 means minus 2. The solution to the equation x plus 3 is equal to 1 cannot be had in the set of natural numbers or in the set of whole numbers. That's why they defined another set of numbers including the negative numbers 0, 1, 2, 3, 4, etc., etc., infinitive, and they included the negative numbers to these minus 1, minus 2, minus 3, likewise up to minus infinitive. And if you keep them in a set like this, minus infinitive, etc., etc., minus 3, minus 2, minus 1, 0, 1, 2, 3, etc., etc., infinitive, plus infinitive. So this set, if you see well, if you observe well, we can find the natural numbers from 1 to infinitive, and we can find whole numbers 0 to infinitive, and in addition to these two, we find the negative numbers. See, the solution to this equation x plus 3 is equal to 1, that is x is equal to minus 2, is found in this set. This set is known as Z and called as integers. The set of integers. If you write these numbers like this, you call them as integers. If you put these numbers in the set is known as integers. Okay, so this is the way they developed these integers. Later on, they need some other numbers to find the solution of equations of this type. 2x plus 1 is equal to 4. 2x plus 1 is equal to 4. Let us find the solution to this one. 2x is equal to 4 plus 1 becomes minus 1. 2x is equal to 4 minus 1, 3. X is equal to 3 by 2. See here, this is a fraction. 3 by 2. But 3 by 2 cannot be found in the set of integers, in the set of whole numbers, in the set of natural numbers. Quite obvious, these are not fractions. So they need another set containing fractions. And then the definition has come for this. How they defined this one, you see. It is in the form of, you see, there is a numerator and denominator. That's why they kept this number like this, P by Q. This is in the form of P by Q. P is an integer, 3 is an integer. It can be integer, whole number or natural number, it may be. 3 by 2, both are like that. P and Q are integers. And they defined like P by Q. So the definition has come like this. A number of the form P by Q where PQ are integers. PQ are integers. PQ are integers. And they put another condition also, which is very vital. CQ must not be equal to 0. Q must not be equal to 0. Q should not be 0. Then normally we think if it is not equal to 0, they define like that. Why can't this be equal to 0? Let us see what happens if it becomes 0 and see the results. So if you want to keep this one in the set form, okay, we get to that later. Let us write first in the set form. Set of all numbers in the form P by Q, where PQ are integers and Q is not equal to 0, they write this type of numbers, or they called this numbers, this set of numbers, as rational numbers. This is called as set of rational numbers and denoted by Q. The set of rational numbers. Set of rational numbers. That means what type of numbers are there in this set? Let us discuss a little bit. As I said earlier, Q should not be equal to 0. That has to be kept in mind. Let us see what type of numbers should be there. Let us write a few rational numbers. 2 by 5 is a rational number. 2, 5. 2, 5 are integers and 2 by 5 is a rational number. Minus 3 by 7 is a rational number. 6 by 7 is a rational number, or minus 6, whatever it is. So these are okay. This is what we think. If Q is equal to 0, what happens? Let us see. 1 by 0. 1 by 0. If Q is taken as 0, it is 1 by 0, which cannot be defined in mathematics. We don't have definition for this. 1 by 0 is considered as infinitive, undefined in fact. Likewise, it is undefined. That's why q should not be 0. See, for example, 2 by 0 if you write, that is also undefined. If you write 0 by 0, that is also undefined. So 0 must not be the denominator. That's why in the earlier stages we understand that division by 0 is not defined. Division by 0 is not defined. That one you have to keep in mind. Now let us see a few more results. 2 by 1, is it a rational number or not? 2 is an integer, 1 is an integer. Otherwise you can call them natural numbers. 2 is a natural number, 1 is a still 2 by 1 should be a rational number because it is in the form of p by q, where q must not be equal to 0, but q is not equal to 0 here. So 2 by 1 should be a rational number. That means 2 by 1 is nothing but 2. That means every natural number is a rational number. Minus 3 by 1, that is equal to minus 3, which is also called as rational number. That means every integer is a rational number. That means you have to understand the set in a wide sense. Rational numbers include fractions, natural numbers, whole numbers, and integers. Now, this is the name of the present chapter, that is rational numbers. So, rational numbers. This is the name of this chapter, rational numbers. We are going to discuss the properties of rational numbers. First, let us see, for better understanding, let us discuss these properties in an order. First, let us see closure property. Closure property. Closure property. Let us take the set of natural numbers first. N is equal to 1, 2, 3, 4, etc. Up to infinity. But closure property or any property, if you take and we check the closure property with respect to addition, multiplication, subtraction, and division. Addition, subtraction, multiplication, and division. With respect to these four fundamental operations, we see that whether the set is following the closure property or not. I am calling it as a set. If you simply remove the set symbol, these are called just natural numbers. If you put them in a set, we call it as a set of natural numbers. That's all. Let us see how closure property is to be checked. Take any two natural numbers. Let us take whatever natural numbers you take. 3, 4 are taken. 3, 4 are two natural numbers. Natural numbers. 3, 4. Then with respect to addition we are discussing. So 3 plus 4, that is equal to 7. With respect to addition we are discussing. So 3 plus 4, we performed the operation addition. 3 plus 4, what is the result? 7. 3, 4 are taken from this set. The result of this one, 3 plus 4, is 7, which is also found in this set. So 1, 2, 3, 4, 5, 6, 7. Next number comes. Next 7 comes. Because we kept dots like this. But 7 is there in the set of natural numbers. Do you understand this one? 7 is also present in the set of natural numbers. If two numbers are taken from this set and their sum is also there in the set, then the set is said to follow the closure property. Or otherwise, you can call it as the set of natural numbers is closed under addition. Okay. The set of natural numbers, natural numbers is, since we write set, we are using is, the set of natural numbers is closed under addition. Okay. Definition of this property is written like this: if A, B are any two natural numbers, if A, B are any two natural numbers, if the sum of A and B, that is, you read this one as that is, A plus B is a natural number, then natural numbers are said to be closed under addition. Okay, this is the way we define the closure property under addition. Now let us discuss the closure property under subtraction. WRT stands for with respect to. WRT stands for with respect to. Let us take numbers. Let us take two natural numbers. 3, 4 are two natural numbers. Are two natural numbers. Then what is 3 minus 4? Because you see, with respect to subtraction, we are discussing this property. 3 minus 4 is minus 1. 3 minus 4 is minus 1, which is not there in the set of natural numbers, because natural numbers start from 1, 2, 3 likewise till infinitive. So minus 1 is not present in the set of natural numbers. 3, 4 are natural numbers. Okay, 3, 4 are natural numbers. But their subtraction, when you do subtraction, the resultant minus 1 is not present in the set of natural numbers. So, set of natural numbers is not closed with respect to subtraction. If you want to take another example, if you take 3 minus 3, that is equal to 0. 0 is also not present. See, for example, 3 minus 3. 3 or 2 times you have taken 3. Then 3 minus 3 is 0, which is not there in the set of natural numbers. Likewise, it goes. And for some other numbers, 4 minus 3, if you take 4, 3, you take 4 minus 3 is equal to 1. 4 minus 3 is equal to 1. You are right. 4 minus 3 is equal to 1. 1 is present in the natural numbers. But see, if any property is to be defined or is said as worked out, if all the cases come true, that means for all the numbers it should be true. In this case it is okay. In this case it is not okay. In this case it is not okay. If it fails in one case, the property is said to be failed. Set of natural numbers is not closed under subtraction. Okay. Now let us see the definition. Closure property under subtraction. If you want to define, you write like this. Let A, B are two natural numbers. If A minus B is also a natural number, then the set of natural numbers is said to be closed. Closed under subtraction. You remember this one. Closure property under subtraction. That's why the set is said to be closed under subtraction. If you don't involve the word set, you can say natural numbers are natural numbers are closed under subtraction. You can call it like that. Let us now discuss closure property with respect to multiplication. Closure property with respect to multiplication. With respect to multiplication. Multiplications, we have to perform operations and see. Now, as usual, from the set of natural numbers, we know what is the set of natural numbers. 1, 2, 3, likewise till infinitive, the set of natural numbers exists. 1, 2, 3 up to infinitive. Take any two. Let us take 4, 5. These are natural numbers. Any two you can take. And now perform the operation multiplication. 4 into 5, that is equal to 20. With any two natural numbers you take, 7 into 3, 21. The result is found in the set of natural numbers, 20 or 21. For example, 100 is a natural number. 100 into 3, that is equal to 300. That 300 is also a natural number. So without any doubt, we can understand that natural numbers are closed under multiplication. So we can say natural numbers are closed under multiplication. Set of natural numbers, if you say set of natural numbers is closed, we call. Instead of or we use is. Natural numbers are closed under multiplication with no doubt. Be clear of that. Natural numbers are closed under multiplication. Okay. If you want to define property, we can say again a definition like this. Definition. How do you write the definition? Let A, B are two natural numbers and if A into B is also a natural number, we say that N stands for set of natural numbers. N is closed under multiplication. Okay, now let us discuss the property under division. Closure property with respect to division. With respect to division, in the same way we perform the operation. Set of natural numbers 1, 2, 3, 4, 5, etc. up to infinitive. Take any two. 4, 5 let us take and perform division. 4 by 5. Is it there in the natural numbers? No, 4 by 5 is a rational number which is not there in the set of natural numbers. Is not a natural number. Okay, it is not a natural. If one case fails, that is enough. We can say that the set is not closed under division. Need not discuss many examples. If one case fails, that is enough. Say set of natural numbers is is not closed under division. So, set of natural numbers is not closed under division. This is how we understand the properties. And initially we discussed the property, closure property, with respect to addition, subtraction, multiplication and division. That is what we did in this video. Well, thank you for watching this video. In this video, we discussed the closure property with respect to addition, subtraction, multiplication and division for the set of natural numbers. We shall continue the class in the next video. Share this video to your friends and subscribe to my channel so that all my videos will come to you.